Now we said in the previous video that the solution to the Euler-Lagrange was always in the same format, that is y equals some function of x and two parameters c1 and c2. Now the accessory equation can be written in a standard format as well. So this is the standard format here. We've got the solution, which is u of x, but the u of x can be made up of a linear combination of u1 of x and u2 of x times a constant factor beta 1 and beta 2. Now we also know that u of x is equal to 0 whenever x is equal to a point A, and it's also equal to 0 at the conjugate points. So we can rewrite this equation with this in, and we can say that 0 is equal to b1 u1 of A plus b2 u2 of A. So we can rearrange these two equations, and we can write that minus b2 upon b1 is equal to u1 of A upon u2 of A, which equals u1 of x upon u2 of x. Now we've seen from a previous video as well that the solution u1 of x and u2 of x can be written in terms of the parameters c1 and c2, which we found from the Euler-Lagrange equation, and such that the u1 of x is partial y by, let's just say, partial c1 and partial y by partial c2. So the little partial in there. So it means then that we can find all the x coordinates of the solutions, that is the conjugate points, if we follow the route here. So we're going to have partial y by partial c1 divided by partial y upon partial c2. That's the ratio of these two here is going to be the ratio of our partial y by partial c1 upon partial y by partial c2 at a point where x is equal to A. Now it might not mean an awful lot here in this derivation, but we're going to use this little equation now and again over the next few videos whenever we come to looking at examples of finding the conjugate points using the analytic method. So that's all for this video. I'll get you on the next video. Goodbye.